Algebra by Michael Artin. Chapter 2, Groups. Section 6, Cosets. One can define cosets for any subgroup H of a group G, not only for the kernel of a homomorphism. A left coset is a subset of the form 6.1 AH equals the set AH such that H is a member of H. Note that the subgroup H is itself a coset because H is equal to 1H. The cosets are equivalence classes for the congruence relation. 6.2. A is congruent to B if B equal AH for some H a member of H. Let us verify that congruence is an equivalence relation. Transitivity. Suppose that A is congruent to B and B is congruent to C. This means that B is equal to AH and C is equal to BH prime for some H and H prime a member of H. Therefore, C equal AHH prime. Since H is a subgroup, HH prime is a member of H. Thus, A is congruent to C. Symmetry. Suppose A is congruent to B, so that B is equal to AH. Then A is equal to BH inverse, and H inverse is a member of H. And so B is congruent to A. Reflexivity. A equals A1, and 1 is a member of H. So A is congruent to A. Note that we have made use of all the defining properties of a subgroup. Since equivalence classes form a partition, we find the following. 6.3. Corollary. The left cosets of a subgroup partition the group. 6.4. Note. The notation AH defines a certain subset of G. As with any equivalence relation, different notations may represent the same subset. In fact, we know that AH is the unique coset containing A, and so 6.5, AH equals BH if and only if A is congruent to B. The corollary just restates 5.4. 6.6, if AH and BH have an element in common, then they are equal. For example, let G be the symmetric group S3 with the presentation given in 1.18. G equal 1 x squared y xy x squared y. The element xy has order 2, and so it generates a cyclic subgroup H equal 1, xy of order 2. The left cosets of H in G are the three sets 6.7. 1, xy equal H equal xyh. The set x squared y equal xh plus x squared yh. The set containing x squared y equal x squared h equal yh. Notice that they do partition the group. The number of left cosets of a subgroup is called the index of H in G, and it is denoted by 6.8 G:H. Thus, in our example, the index is 3. Of course, if G contains infinitely many elements, the index may be infinite too. Note that there is a bijective map from the subgroup H to the coset AH, sending H to AH. Why is this a bijective map? Thus, 6.9, each coset AH has the same number of elements as H does. Since G is the union of the cosets of H, and since these cosets do not overlap, we obtain the important counting formula, 6.10. The order of G is equal to the order of H times the index G:H, where the order of G denotes the order of the group, as in 2.10, and where the equality has the obvious meaning if some of the terms are infinite. In our example 6.7, this formula reads 6 is equal to 2 times 3. The fact that the two terms on the right side of equation 6.10 must divide the left side is very important. Here is one of the conclusions stated formally. 6.11. Corollary. Lagrange's theorem. Let G be a finite group and let H be a subgroup of G. The order of H divides the order of G. In section 2, we define the order of an element A, a member of G, to be the order of the cyclic subgroup generated by A. Hence, Lagrange's theorem implies the following. 6.12. The order of an element divides the order of the group. This fact has a remarkable consequence. 6.13. Corollary. Suppose that a group G has P elements and P is a prime integer. Let A, a member of G, be any element, not the identity. Then G is the cyclic group 1, A, A to the P minus 1 generated by A. For since A is not equal to 1, the order of A is greater than 1, and it divides the order of G, which is equal to P. Hence, it is equal to P. Since G has order P, the set 1, A, A to the P minus 1 is the whole group. Thus, we have classified all groups of prime order P. They form one isomorphism class, the class of cyclic groups of order P. The counting formula can also be applied when a homomorphism is given. Let phi, mapping G to G prime, be a homomorphism. As we saw in 5.13, the left cosets of the kernel of phi are the fibers of the map phi. They are in bijective correspondence with the elements in the image. 6.14. The index of G kernel of phi is equal to the order of the image of phi. Thus, 6.10 implies the following. 6.15 Corollary. Let phi mapping G to G prime be a homomorphism of finite groups. Then the order of G is equal to the order of the kernel of phi times the order of the image of phi. Thus, the order of the kernel of phi divides the order of G, and the order of the image of phi divides both G and G prime. Proof: the formula is obtained by combining 6.10 and 6.14, and it implies that the order of the kernel of phi and the order of the image of phi divide the order of G. Since the image of phi is a subgroup of G prime, the order of the image of phi divides the order of G prime as well. Let us go back for a moment to the definition of cosets. We made the decision to work with left cosets AH. One can also define right cosets of a subgroup H and repeat the above discussion for them. The right cosets of a subgroup H are the sets. 6.16. HA equal the set HA such that H is a member of H, which are equivalence classes for the relation, right congruence. A is congruent to B if B is equal to HA for some H a member of H. Right cosets need not be the same as left cosets. For instance, the right cosets of the group 1, xy of S3 are 6.17. The set 1, xy equal H equal HXY. The set x, y equal HX equal HY. The set x squared, x squared y equal HX squared equal HX squared y. This partition of S3 is not the same as the partition 6.7 into left cosets. However, if n is a normal subgroup, then right and left cosets agree. 6.18 Proposition. A subgroup H of a group G is normal if and only if every left coset is also a right coset. If H is normal, then AH equal HA for every A a member of G. Proof. Suppose that H is normal. For any H a member of H and any A a member of G, AH is equal to the quantity AHA inverse times A. Since H is a normal subgroup, the conjugate element K equal AHA inverse is in H. Thus, the element AH equal KA is in AH and also in HA. This shows that AH is a subset of HA. Similarly, AH contains HA as a subset, and so these two cosets are equal. Conversely, suppose that H is not normal. Then there are elements H a member of H and A a member of G, so that AHA inverse is not in H. Then AH is in the left coset AH, but not in the right coset HA. If it were, say, AH equal H prime A, for some H prime a member of H, then we would have AHA inverse equal H prime a member of H, contrary to our hypothesis. On the other hand, AH and HA do have an element in common, namely the element A, so AH can be in some other right coset. This shows that the partition into left cosets is not the same as the partition into right cosets. Algebra by Michael Artin, MIT. This book was published in 1991 by Prentice Hall. It is read by Jim Renholt with programming and illustration by Jim Renholt, 2019. Thank you for listening.